this tutorial is to learn you to make XANES and eventually some other spectroscopy simulation, ab initio simulation. And to start, I'll have a very small presentation, maybe 10 minutes, something like that, to explain a bit my philosophy. And I guess you also follow the course this morning about XANES, so you know different things. So my bibliography, so there are different papers and books you can see, and very recently you can note, so you have this document, in fact, in the package you must have a download in any case. And at the bottom, you can see that there is a new volume of the International Tables of Crystallography. So you can get information about the code FDMNES in this new volume. Okay. So before making simulations, we must know what kind of code you can use, because the different code to make simulation of XANES spectroscopy use different theory, and some are adapted to some edges and some other are adapted to other edges. In fact, there is two cases, depending on what is probed by the photoelectrons. There is two cases. So first cases, typically at the L2-3 edge of the transition element, of the 3D elements, you probe, in fact, localized state, for example, 3D state. In the case, so at this L2-3 edge, for example, you can see on the left, you have the nickel edge in the nickel oxide, and you can see the edges, they are very sharp with a very high white line, and then that go back nearly to zero. Then you have the second edge, L2, like this. So in that case, this means that your states, the probed state, are localized, you can see in energy, and they are at the same time localized in space, because the 3D orbitals have a small radius. Okay, in that case, you can use different theory, but the most often used is in fact a multiplex ligand field theory to simulate these edges. In the other cases, your final states are not localized. It's typically the case of the K edges, for example. You can see this tape-like shape. It means that your probed states are not localized. It's a wide band. And it's typically the case when you probe a P state, for example. So in that case, you can use ground state theory or nearly ground state theory, typically DFT, for example. And unfortunately, you have the worst cases when you have a big white line, but after the white line, the intensity doesn't go back completely to zero, and then you have a second edge. This is typically the case of nickel L2-3 edge in nickel metal. So depending on these three situations, you have different theory to do that. So the first one, for the first cases I already mentioned, is the multiplex ligand field theory. So it's multi-electronic, but monoatomic, in fact. So you don't consider you only consider the symmetry on the absorbing atom, and with some parameters, you can simulate the different edges. But it's essentially monoatomic. So it's the case of the L2-3 edge of 3D elements, but also of the M4-5 edges of rare earth elements. And in all the other cases, you can use DFT approaches. So it's for the K or L1 edges of all the elements, or the L2-3 edges of heavy elements. And in the intermediate situations, you need to be at the same time multi-electronic, but also multi-atomic, like can do DFT. So you have to use deeper theory. You have different, very different one, using Peter-Salpeter equations, time-dependent DFT, and so on, techniques. And they are developed by different people. In fact, in my code, you have also the time-dependent DFT. So now it's interesting to see how we can reach the monoelectronic XANES formula. Maybe you have already seen it in the course this morning, but it's interesting to see the difference between how we go from the multi-electronic case to the mono-electronic cases. So we consider we have a systems which is multi-electronic. So I, it's the initial state with all the electrons, and F is the final states with all its electrons. And this one is a formula to get the cross-section. H bar omega is the energy of the photon, and alpha is just the fine structure constant. O is the operator to make the transition between the initial state and final state, and probably you have already seen that it can be written as a dipole part. Epsilon is a polarization of the incoming field, R is a position, and here the quadrupolar part. So you have again the polarization and then the wave vector. So there are different selection rules applying on these different parts. Now, to go from this multi-electronic situation to the monoelectronic situation, in fact, we consider that in I, we are interested only by the state where come from the electrons, the one making the transition. So G, little g here, will be, for example, the 1s state, so the core electron making the transition. Then you have the transition up to F, which is a specific stage, specific orbital, where arrive, make the transition, so the photoelectron. O is the same as before. And in fact, all the other electrons in the atoms or even in the molecules are considered not, they are just considered as following our the general effect. So in fact, there are some effect, and for example, the other electron in the absorbing atom slightly contract after the transition to screen the core hole, and this contraction, in fact, gives this factor SO square that you have probably seen already in XAS, but it's a constant. And also all the other electrons, because they contract down to the core level, so they lose some energy, so there is a variation of on energy. And often, in fact, when you look at the formula, we forget these two terms, but in fact, they are there. So now F is by default calculated in an excited state. In fact, that is with a core hole. There is this, for example, 1s core hole, and you have also an extra electron on the first non-occupied level. So now you have this formula a bit simplified, and in practice you make this calculation, but you have also to take into account of the core hole lifetime. To do that, you have to make a convolution through a convolution, through in Lorentzian function, and in fact the width of this Lorentzian, so it's due to the width of the core hole, but also the width of the photoelectron state. And this one depends on energy, because if you are close to the Fermi level, it's 0, in fact, this value. And when you increase in the kinetic energy of the photoelectron, so you can excite the plasmons and different phenomena, and so this broadening increase. Okay, so we have seen so XANES spectroscopy, and the code, in fact, can also calculate a related spectroscopy, such as X-ray Raman scattering. So in that case, you have an inelastic process, and the difference in energy between your incoming photon and your outgoing photon is close to the energy edge. So if you vary this difference in energy, in fact, you go through all the edge, and you can demonstrate that at the end, the outgoing intensity is related to this classical edge we can see. So it has been discovered now a long time ago. It can be recorded also at the ESRF on ID 20. So there are different things in the formula. Maybe what is only important to show is that, in fact, in that case, the transition look in that way. And if you consider that QR is small in front of 1, you can make an expansion, and you can see that the formula at the end is very close to the one used in XANES. You just replace polarization by Q, and at the end, you get more or less the same things. But in fact, we can go a bit further, and the difference with XANES is that you can also have a monopole term, that is a transition which is delta L equals 0, which makes that you probe not only the dipole term, but also the monopole term plus the quadrupole term. And it can be interesting in some cases because you can so see specific features that you cannot see in classical XANES. So the code can also calculate this kind of phenomena. Another thing that the code can calculate are the emission spectroscopy, and more specifically, the valence to core emission spectroscopy. Here, there is an example of calculation. So now what you probe are in fact the state below the Fermi level, and the formula, in fact, to go down in energy from the occupied state. In fact, the formula is exactly the same or nearly the same than for XANES. So in the code, it's rather easy to calculate also that. And here, I want to mention that the code, in fact, can also calculate the density of state projected on the atoms, and also this scope, that is the crystal orbital overlap population. So in the output of the code, so you can have the classical spectra, XANES or XAS, but here, but you can also have the density of state projected on the different atoms. For example, here are the density of state of oxygen for the S state and for the P state. And if you look at the spectra, you can see that here, where you have this bump, you can, in fact, there are also some S state of the neighboring atom. The calculation is done here at the zinc K age in ZNO, I forgot to mention. And because the code can also calculate the scope, that is the overlap between different orbital making a molecular bond like this. In fact, you can calculate this integral here, so you can calculate the covalency, if you want, between two atoms. So it's what is done with this result, and you can see here the result that, in fact, this bump is due to this molecular bond between the zinc atom, the zinc P orbital, and the oxygen S orbital. Okay, and here it's some experiment, and it corresponds more or less to the experiment. So what is important to mention is that the code can calculate not only the XANES spectra or the emission spectra, but also make easier the analysis, showing what state participate to such a bump in your spectra. The code can also calculate resonant X-ray diffraction. So in that case, the photon comes in and then is immediately emitted, and in a resonant way. So you probe the same state, but you go back to the ground state for the electron. So evidently, because you have the same kind of transition where you have an absorption edge, you have the intensity of some diffraction peak, which change around the absorption edge. So it's resonant diffraction. The formula is this one. You can see that you have this transition from the core state to the final state, and then you go back to the core state. So we can understand that results are in some way similar. The difference now with the XANES is that you don't simply sum over the absorption of the different absorbing atom in the unit cell, but you have also to consider the non-resonant term, the Thomson one, the magnetic one, if it's magnetic. And you have to consider also the Bragg factor, which makes that for some peaks, you are at a forbidden reflection, which makes that intensity is 0 far from the edge, before the edge, and 0 far above the edge. And so you can have intensity just at the edge, so you can study many physics with that. The code can also calculate surface resonant X-ray diffraction. So in that case, you have a surface with some crystal, some films on it eventually. And in fact, in that case, Bragg peaks are not anymore simple points in the reciprocal space, but you have a truncature rod. And so all the values are possible if you take L as these directions. In fact, you have intensity also between the bulk Bragg peak. And for example, we did that on an iron, on a magnetite compound crystallized on silver. And you can see the effect. So we can get this intensity. And here you have at the same time the calculation and the experiment in dot. And you can see that we can reach also a convenient agreement. Okay, so we saw all the spectroscopy we can calculate and about the technique of calculation. So what is complex, in fact, in our approach, so using DFT, is to complex the final state. So it can be in different ways. So it's known for a long time from the 70s how to do that, more or less, after we have a lot of improvement. First two calculations are from the 80s by Nathalie, principally. And now the way how to calculate this F, in fact, you can calculate in all way you can. You can use the 3D periodicity, so use the bond structure calculation, but you can also perform the calculation using a cluster approach, like if it was a molecule. So you make a cluster around the absorbing atoms, as do FDMNES. And after, to solve this space in 3D periodicity or in the cluster, you can use different theory. All the methods are possible. The most often used in XANES is the multiple scattering theory. And so it's done in the FDMNES, but in FDMNES, the name FDM comes from finite difference method, because there is also the second method, which is more precise than the first one. That's the multiple scattering theory. So the multiple scattering theory, so it's something rather simple in the philosophy. So to calculate the final state, we develop, in fact, this calculation in a path between the different scatterers, I would say. So if you consider all the paths, it means that you have to calculate such equation where they are the atomic scattering amplitude in all the atoms. H are the paths between the different atoms, the probability to go from here to here, for example, more or less. And if you solve this, in fact, you consider all the possible paths. And at the end, you have the multiple scattering amplitude. And the multiple scattering amplitude is related to the amplitude in the absorbing atom by this way. So in all the atoms, you can have such a development. So you say that the wave function, so it's a spherical harmonic, the dependence over the angles. Then you have the radial solution of the Schrödinger equations and times an amplitude which depend on the energy. And it's, in fact, it's in the amplitude modulus square which is proportional to the density of state. In fact, the shape of the signal depend on A. And so the multiple scattering amplitude is related to directly to this value. So, and at the end, the cross sections can be rewritten in that way versus multiple scattering amplitude. And for people who like mathematics, this guy here is the green solution. So this technique is relatively fast, but very often used. Unfortunately, it uses most often the Muffington approximation on the potential. So in this approximation, the potential is constant between the atom and spherically average inside the atoms. And we can understand that it's an approximation versus the true potential. And specifically, if you are at a very low energy, that is just at the edge energy or at some EV above the energy, or if your material is not dense or very aspherical, it's the approximation can be rather bad in that case. So the second method, so it's a finite methods. So in fact, in that case, to solve the Schrödinger equations, you just make a grid of points. You develop the Laplacian, so the second derivative in each direction, in each point, considering, for example, on this point, the value of the wave function on the different neighboring points. So the second derivative is this one, h is in interpoint distances. You put all that in the Schrödinger equations, and at the end, you can solve it. So you get the value of the wave functions everywhere on all the point of the grid. You have special function at the border. And okay, and after you solve that. So the problem is that to have a precise calculation, your density grid your grid must be dense, so you have a lot of points. So it's longer, it takes more time, it's more consuming than the multiple scattering theory, but it's more precise. And fortunately, for some years now, we collaborators in Russia make that part of the code far more faster than before. So now it's possible, in fact, to calculate also with theory, even if it's always a bit longer. So now FDMNES, the code, so my code versus the other ones. So FDMNES use, as I said, DFT, time-dependent DFT, if you want to be a bit more precise for L23 edges. It uses multiple scattering theory, finite difference method, and also it's self-consistent, what can be important. So in fact, when you want to make this kind of calculation, so you can be cluster approach or with 3D periodicity, so you can do your market and also try other code if you're interested by. So the main characteristics that the code is ab initio, so it's for all these spectroscopy. As I said before, you can download it. It's the old name. Okay, so it's fully relativistic with spin orbit, if you ask for. So it uses a cluster approach. There are these two techniques. So it's DFT, but you have also the U-bar correction. Sometimes it can be important for oxide or specific compounds. And you have also the time-dependent DFT. About the cluster approach, sometimes it's surprising that calculation can be done just for a cluster, even if we have a 3D material. So, in fact, both approach, using bond structure, using the periodicity, so working in reciprocal space, or cluster approach are equivalent if the cluster dimension is sufficient. So in practice, we make first calculation always with a small radius around each absorbing atom in the unit cell, and then we increase the radius up to conventions. And fortunately, because the photoelectron is inelastically scattered by the neighboring atoms, we don't have to go up to infinity. And in practice, you have to go up to 5, 6, 7 angstrom typically, and it's very rare that you have to go further. Yes, just to note that the code, so it can be run on a PC, as you have here, but it can also be run on a cluster of computers, and the code is in fact installed in many synchrotrons at the ESRF, for example. So there are different way how to run it. But okay, if you don't know, the best is to ask to the informatician in your center of calculation to explain how to run the calculations. Now, what is important to know is that fortunately there is a manual, a user's guide, which come with a package. So you can see many things that I've said, but also you have many explanations on how make the calculations. So most calculations need rather few information, but in fact you can do far more. And what you can do depends of what you want to do. And it's done thanks to keywords that you have to specify in your in-data file. And the list of your keywords with what they do are given at the end of the user's character. And also rather close to the end, very importantly, I've written 2 or 3 pages, so it's rather short. So some advices to make the best possible simulation. So please, if you have never done, before making calculation, read these 2 or 3 pages. So it's some of the points will be, I go to explain them during the tutorial, but it's good to see that, how to make the best possible simulation. Okay, now we go to enter in the in the most important part. So how to make simulations. So the code will be in your computer, and you have to know that the code uses 2 in-data files. FDM file.txt, we'll see after what is in it. In fact, there is just the name of the main in-data file, and the main in-data file where you have all the information you need for the calculation. So you run, clicking on the executable. If there is some mistakes, so if the program stops immediately, just check if in the same directory you got this FDMNES _ error file. So if there is no problem, so that go up to the end, and you will see appearing some output files. Usually you have just 3, these 3 here with a specific no extension, with BAV extensions, or with CONV expansion. So it's the same than this one. Here, the output are here, the main output, the spectra you want to calculate, and this one is before convolution, and this one is after convolution. You remember that we had to make some convolution. Okay, and about the in-data file, so we'll see after, but I show. So it's the main in-data file. So you have 2 types, I would say. So you can see first that to make a simple calculation, you don't need many information. In fact, you need just what is also important when you make the experiment. So you have to give an output file name with a directory eventually. If you want your output in a subdirectory, you have to define the energy range. So it's in EV, and like in the experiment, in fact, we can note that it's important to have a thinner step at the beginning of the edge than at the end, because the feature are you have more feature at the beginning. So we do the same in the simulations, and here, for example, from -2 at 0 is the Fermi level, so it corresponds more or less to the edge energy. So you start at -2, you have a step of 0.1 EV up to 0, for example here, and then you have a step of 0.5 EV up to the final energy 60 EV. Then you remember that we had to define a radius, and we consider only the atoms inside this radius. In that case, it's a little molecule, so we just need to have a radius bigger than the molecule. Then different keywords. This one is optional. So if you have not the quadruple keyword, we will calculate only the dipole that is a main contribution. And here, if we want to have, it's optional also this one, it is if you want to consider different polarizations along the different direction of the incoming field. Then you have to define your molecule. So 3 multiplicative number along the 3 directions. So it's like A, B, C, if you want, it's in angstrom, and the angles between the different directions. So here it's orthonormal. And then you put all your atoms. First is the atomic number. So 23 is vanadium. And then this one is at the center, 000. the oxygen is along 1, so times 2.16 angstrom along X, this one in the other direction, etc., along Y and Z. So you can see it's an octahedron. And then if you write the keyword convolutions, you will have also the convoluted spectra, and we finish with N. The other kind of in data, if you want, is a crystal case. So now you have not any more molecule, but a crystal. So it's defined more or less in the same way. So you have A, B, C, the unit cell parameter, the angles, and the different atoms, the non-equivalent atom in the unit cell. And because, and in that case, because we have just written the non-equivalent atom, you have to define the space group with the name of the space group in accordance with the international table of crystallography. And here are special keywords if you're interested by DAFs or resonant diffraction. So maybe we'll see later if you're interested. Okay, yes, and for absorption of 4 diffractions, that doesn't matter. Sometimes it's good to consider, here we have defined all the atom position, but if you have the structure from CIF file or PDB file, you can just call in some way this CIF file. So using this keyword CIF_file, and then where is this file in your computer? So the reading will be automatic. Okay, so it finished this part very well. So I hope you have downloaded the package.
Yes.
Okay. So so you can see opening it. So you unzip it. So you have the code. So in the for the different type of operating system you have. So for Windows 64, Windows 32, Linux, or Mac. So you can keep just the one you are interested by. If you use Mac, you have to run this command. It's just a way to say where is the code to make it that running directory. This one. Okay. So to run, you remember I said that to run the code, I have a Windows 64 PC. So there is this file. So the code, when you run, open this file. So I just open it just to show. So you can see it's very simple. In fact, you have just the number of a job you want to do, and then where is this the true in data file. So in fact, I do that because well, it's more easy in practice. And also, for example, if you want to make a different calculation during the night, for example, you can run maybe, for example, 10. And give 10 input file name below. So you will have all this job done automatically, one after the other. Okay, now, so it was in Sim and in practical, I guess, I hope it was the case. So the data file is this one, so it's very close to what you saw just before. So the energy range is not exactly the same, but it will go up to 100. And you can see I can use different steps and I'm increasing the step each time. And this guy, it's so its calculation is between -5 up to 100 EV. But just for the convolution part, you can start at lower energy to, if you want to compare to the experiment, sometimes it's good to start at lower energy, and that costs nothing to start at lower energy at this. So you can see I have the keyword quadruple, so we go to run this, just simply this. Okay. So it will. Okay, so to run, so you can do the same, you just click on it. And okay, if you have this screen, it means that the code is new on your computer. And so it's me who wrote it, so you can be sure that you can run it anyway. So I run it anyway, so it will be asked only one time. So it's running, you can see it's finished. So I hope it was okay also for you. And now we go to look at the results. So to do that, you have to use some code to plot. Me, I use Calibration, but it's just my test. So the output are here. You can see now you have these 3 output files. I can just open just to show. So you can see the energy versus the cross section. Cross section is in megabarn. 1 megabarn is 10 to the minus 18 centimeters square. Here there is a specific line necessary for the convolution part. So when you plot, you have to think that you must consider it. You have to eliminate in some way, but for the convolution you need it. Okay. The one which is convoluted, it's with this underscore conv, so it's the same, but without the first line. And the BAF file we'll see after. So I go to plot this one, the not convoluted one, so do the same. I skip the first line. And I also go to plot the convoluted one. So I don't skip. Okay. So what is good to see, it's both together. So the convoluted one and the not convoluted one. It's to see the difference. Okay, so you have this big first peak, but okay, I zoom a bit. So I hope you can have this. Sometimes it takes sometimes to to do that at the beginning. If I need to wait, you just say, send a message, or just say, no, nobody. Okay. So the first things you can see is that the effect of convolution is big. The effect of this width is very important. So this one is a convoluted one. The second thing is this big peak in the not convoluted file. You can see it's below 0, and 0 is a Fermi energy. So this one is here. In fact, they are in occupied state, so below the Fermi energy. So in the first part of the calculation, the code calculates all the transition without considering, in fact, the Fermi level. So you make transition also towards occupied state, what is not possible. So the convolution part not only made the convolution, but put also to 0 all the transition below the Fermi level. So it's why this one disappears after the convolution. Okay. So if you are not used with XANES spectroscopy, for people who are used to do that, experimentalists and so on, when they see such edge, you see with a little white line with some shoulder here, and then some dip in that part, and then other bump. In fact, it's typically this shape of octahedral environment around the absorbing atom. So when you see that, you can be pretty sure that the absorbing atom is inside an octahedra. So the shape is really a signature of the local geometry and the local symmetry in general. Okay, now we could go a bit further. If you look at here, in fact, you have these two bumps in the convoluted spectra, and here we can see better is the not convoluted spectra. So it could be interesting to see what they are. Now I go back to the in-data file. So it's here. We had this keyword quadruple. So I propose to make a new simulation without the keyword quadruple. So to do that, so you can suppress the line, or you can put an exclamation mark before. Yes, exclamation mark make that the line is just a comment. Note also, yes, I didn't say that the format doesn't matter. So you can have a space or that doesn't matter. Capital or small letter doesn't matter. You can write a molecule with that. That doesn't matter. And so on. So you can write a bit more or less like you. The order also of the keywords don't have, doesn't matter. It can be, you could have a radius with a 3 below, just at the end, that doesn't matter. Yes, green keyword, I forgot to mention this keyword before. Green keyword is just to make the calculation using the multiple scattering theory, which use the Green's function, so it's why it's green. If you don't have this keyword, you would automatically be using the finite difference method. So for this tutorial, because we want to go fast, we make all the calculation using the green keyword, that is using the multiple scattering theory. Okay, so this new calculation will be done so without quadruple. So I go to change your output file name. Or you can give the name you want. Don't forget to save the file. Well, so I keep the same in data file. In that way, I don't have to change. You remember this name, which is in fdmfile.txt. And now you can run again. So maybe. So just click here. What I go to make a okay, just to click more quickly. Okay, so now I propose you can compare also now this new calculation with the previous one. So maybe to see better, it's to plot the not convoluted one. So the new output file are here. I plot it with the others. I plot. So there are not many difference, but just at the beginning. And indeed, the difference is only here. So at the pre-edge. So this calculation, the red one, is with quadruple, and this one is without the quadruple. So maybe some of you know what this comes from. So it's due to the selection rule. In fact, the dipole selection rule is delta L equal the difference between the L of the initial state and of the final state is plus or minus 1. So at the k edge, your initial state is 1s, that is L equals 0. So what you probe, plus 1, it's L equal 1, it's a p state. So what are probed in practice for a 3D element? There are the 4 p states. For the quadruple, you could have -2, 0, or +2, but at the k edge, it's only +2 delta L. So it means that from a 1s state, you can probe the L equal 2 state, that is a D state. And in practice, it's a 3D state. So here, you can see the two 3D states around the vanadium, because it's a vanadium KH we are probing. And the one of you who, some of you know about solid state physics or symmetry. And they know that in cubic symmetry, in fact, you have two kinds of D state, the so-called EG state and T2G state. So they are, and they are this one, in fact, if you consider the three orbitals, the 5D orbitals, in fact, three of them are T2G state. So they are the DXY, and the two others by symmetry. And the EG state are the other ones, the dx2 minus y2 and the dz2. So these two last, in fact, have the, if you see the shape of the orbitals, in fact, they point towards the neighboring atoms, the EG state. And due to this phenomena, because it's anti-bonding, in fact, with the neighboring atoms, they are at higher energy than the other ones, with point between the neighboring atoms. So here are the EG state, and here are the T2G state. And because here it's 3 state on times 2 because of the spins, it's more or less 6 place, if you want. And here it's only 4. So it's why this one is bigger than this one. Okay. So me, I know the result, but in fact, you can check if you want. So using the code. So I make a new calculation. In fact, all could have been done together. So I suppress my extension. And if I want to check this, so I take back quadruple, but I said, you remember in the introduction, that it's possible to have the density of state of the absorbing atom. So if I write this keyword, density, I will have the density of state of the absorbing atom in a special output. Note that if I write density all, I will have the one of all the atoms. That is also the one of oxygen. But maybe here I don't mind. So I will have only the one of the vanadium, of the absorbing atom. So I save, I run again. And now, maybe you will see there is a new output, VO6 underscore SD0, like state density, and 0 is for the absorbing atom. Okay, so just open, you can see that energy again, the S state, the integral versus energy, Px, Py, Pz state, and the sum, the integral over energy, and then the different D orbitals, you can see. The sum over everybody times the spin, and the integral versus energy and the total of everybody. Okay, so we could plot this. So we are interested by this energy range to see what are these states. Well, first, I can plot the total of the P state for summarize, and the D state, and the integral over the D state. New plot. So first, about the P state, the black. So you can see that it's very similar to the edge we saw before, to the XANES spectra. It's rather similar, so you can see with this before convolution, but not exactly the same because there is some slope effect like this. So, but what is important is you can check that XANES is more or less proportional through some slope, anyway, through some function, additional function. It's proportional, nearly proportional to the density of state for the P state. Okay. Now, if I look at only the D state, so it's the red one, so you can see that they are all here. There are some after, but we're interested by this one. In fact, here are the two states we have probed before, for responsible of the bumps we had here. You can see. And here, in fact, you have also some here, because here are the anti-bonding state, and this one are the bonding state, but we don't see them in XANES. And moreover, in number of electrons, it's not a lot because it's an oxide. And if you look at the integral is close to 10. It's normal. You have 10 possibilities, 10 3D possibility for the electrons. Of course, it's not occupied, but for vanadium, but the integral must be 10 at the end of the bond in some way. Okay, and now to verify what the orbitals are present. So I suppress the P, I don't mind. So I know the result, so I could, well, I can plot all of them, but in fact, you have only two states, you see. The colors are not exceptional. Bon, the black one is the sum, but in fact, three states are here of the kind dx, xy, and the other one are here, the dz2 and also the dx2 minus y2. Okay, so you can verify in that way where the structure comes from, if you want, in your spectra, and make a true spectroscopy looking what orbitals are probed and so on. Okay. Is there some question or not? No? Okay. Okay, now we go to do different things a bit simpler. It's interesting to get some feeling, to see what happens if you change things in data file. So, well, here I suppress density, otherwise we have too much output file. So I propose we change the absorbing atom. Here is vanadium. Maybe I could mention that you saw that we have calculated the K edge of vanadium and not the L2 edge, for example, of oxygen. So how the code knows that? It's only because by default, the calculated edge is the one of the chemical species first in the list. So it's vanadium. And by default, the edge calculated is the key one. But if you want to calculate another edge, so you can change the atom position, but the other way is you write the keyword Z absorber, and below, so if you write 23, it will be the same. But if you write 8, it will be the one of oxygen. Okay? So but I propose you calculate this. So yes, you have to change the output file name. So VO6, it will be the oxygen edge. Okay. You can suppress the keyword quadruple. You have to know that quadruple are not negligible only if you are at a rather high photon energy, and typically below 40,000 EV. Typically, there is no quadrupolar effect. So at oxygen K edge, you have no quadrupolar effect. So if you keep it, that doesn't mind, in fact, but you can just suppress. So you could run that. So you have this new output file. Okay, I take the convol of not. I go to take the not convoluted one. It's, just to see more the details. So you will see it's very different. So the shape has nothing to do because it's not oxygen is not at the center of an octahedron, so it's completely different geometry. So the shape is very different. And if we zoom here, what is interesting is that you have this feature. And in fact, yes. And well, it's not exactly like I expect before. It's because it. Yeah, sorry, it's because it's the. Yes, I use the convoluted one. I would prefer this one, in fact. The not convoluted one to see better. No, it was a good one. I'm sorry. It was a good one. Okay. What I want to mention is that, in fact, this little peak here corresponds to this state here in practice. So very often at the oxygen edge in a 3D oxide, in a metal oxide, you have a first feature which is very high. It's not like a pre-edged because it's so much high. That corresponds also to some molecular bond with the neighboring metals, in fact. Okay. Well, so it was to say that to show this keyword, the absorber. And now about the edge, so it's by default the K edge. But if you want to calculate another edge, you write the keyword E edge, no edge. And below, so if you write K, it will be the same than the default. But you can write what you want. For example, if you write L2, it will be the L2 edge. Or M4, it will be the M4 edge, or M4. Sorry, M4. It will be the M4 edge. For 3D elements, very often we are interested to have both L2 and L3 together. So if you write in that way, you will have both edges. So you can do it. As I mentioned, so the code is not very good to calculate this kind of edges, but anyway, you can do. So I save. So because it's low energy edge, we don't need quadruple again. And so we run. You have this new output file here. It's a convoluted one. And you can see now this kind of edge. So this one is the S3, this one is the L2. I zoom. And if you compare with this feature, in fact, you can see they are more or less at the same energy. Better say the difference is energy is more or less the same. And it's because we probe the same state. You remember here we were probing the by the quadruple the 3D state, and in fact, at the L23 edge, because of the selection rule delta L equal plus or minus 1, now you probe so the 4S state, but also with delta L equal plus 1, because you start from the 2P state, you probe the D state. So it's why it's more or less the same shape. And this one is for the S3, and this one is for the L2.
May I ask a question, please?
Yes. Yes. Please.
Oh, yes, sorry. So for the spectra that are simulated, I was wondering what is the origin of the first signal that is very below the Fermi level. There is usually a very intense peak, but it doesn't reflect in the convoluted data.
Yes, it was about the beginning, right?
Exactly, yeah.
Yes, indeed, because the code, in fact, is a bit stupid. And in the first part of the calculation, the code calculates all the transition matrix, if you want, all the probability of transition from the 1S, for example, up to the valence state, valence and conduction band state, to all the possible states.
Okay.
And without thinking about where is the Fermi level. It means that also the transition towards occupied states are calculated. So it's what you get in this not convoluted file. And after, in the convolution, he thinks, oh, okay, it's not correct. And so he suppresses what is below 0 in some way. So below what is occupied. And then make the convolutions. So also, why is it done in that way? It's not only because it's stupid. It's because, in fact, what we probe are excited states. And the Fermi level, it's a concept of ground state. And consequently, so because it's a DFT calculation, and we are, in fact, probing some excited state, there is some contradiction. And at the end, the cutting energy or the fine or the true, if we can say, call it, or the Fermi level of the excited state is not well known. So it's why I have let this possibility to calculate this transition toward possibly occupied state, because sometimes, in fact, they are not completely fully occupied.
Okay.
And indeed, in the data file, if you want to check this, in fact, it's in the convolution part. You can say, okay, maybe my Fermi level is not exactly what was calculated by default in the ground state, and so you can add a keyword. So I prefer now to write it like E dot, because Fermi level, because it's an excited state, but it's not exactly the good word. So, and so, for example, you can write so it must be close to 0 in any case, but you can try minus 0.5 or things like that. And sometimes it can be slightly positive also, something, but it must be close to 0. And when you make simulations, you can check at the pre-edge, comparing to experiment, if in fact this improves, if you can see appearing some pre-edge, for example, that you can see in the experiment, and not in the simulation if they are at lower energy. So it's especially if you work on 3D material, it can be helpful, this part.
Thank you. And if I may, I have a second question also.
Yes.
So in the example of this VO6 molecule,
yes.
For example, we can imagine that we want to simulate this for simulating vanadium coordinated by water molecules, I guess.
Yes.
And how do we specify whether it is vanadium 2+ or 3+ that we want to simulate?
Okay, it's a difficult question. No, it's not a difficult question. It's the answer which is difficult. No, so indeed, for this molecule, the idea is it's vanadium in solution. Yes, indeed. And no, first about this problem. So if you compare with experiment, what is surprising is that anyway it's not so bad what we have calculated here. So it's rather surprising because we have neglected the hydrogen atom, and calculation is not self-consistent and so on, and it's not so bad. Now, if you compare with experiment, in fact, some details are not in the simulation, and to have these details, you need to put also the hydrogen atom. Okay, so I did that. So in fact, I have considered the water molecule, and with fixed distance between the hydrogen atom and oxygen, and I've set the hydrogen atom, and indeed, this was improving the shape. Second point, a colleague of me, the Intestemal, have been beyond this, considering, in fact, for water, for vanadium, or it was iron, I think, in fact, for iron in solutions. So you have this local order, but you have also some second shell, highly disordered, but there are something. So he did Monte Carlo simulation and so on. And in fact, has also added, if you want, make the average between all these Monte Carlo simulation with some average of second shell around the absorbing atom. And this was again slightly improving, not the first bump, but the following bumps for this kind of problem. So now about what you said. If you want to calculate some molecule which is oxidized, it depends if it's the molecule which is oxidized or if it's the atom. So normally the program is self-consistent, and the best, in fact, is to make a self-consistent calculation. And if it's well done, which is not always the case, if it's well done, automatically vanadium will be plus and oxygen will be minus in some way, some amount. Okay. Donc, to do that, you just have to write the keyword SCF, self-consistent field. So it will take some more time, but okay, it will be done. Now, if you make a self-consistent calculation on this molecule we have just seen here, it will be worst because we have not put the hydrogen atom. And so, of course, it will be horrible in that case because the vanadium will be too much oxidized, evidently, without the hydrogen atom. So it will be worse. So we must make self-consistent calculation only if we have all the atoms in your structure and relatively in the good position. Otherwise, it's worse. So, okay. Now, the most difficult point is when, in fact, you have your atom in solution, and in fact, the counter ion is around it, but we don't know where. So, in fact, you have to calculate a true charged molecule in some way, because the counter ion, you don't know where it is not in your calculation. So, in fact, it's a more complex case. And to say the truth, I prefer most of it not consider it and do in the same way, in a self-consistent way, if all the atoms inside are considered, than with charging the atoms. Most often it's the best. But nevertheless, it's possible to charge the material. To do that, so, but it's a bit risky if you want. But I explain anyway. If you do want to do that, you have different keyword, atom or atom conf. I use this one, atom conf. In that case, you can say, for example, I think the vanadium will be 2 plus. But 2 plus, it's okay. To say that, in fact, I have to define the orbital where I have the electrons or not. Okay, so below atom conf, you say I go to define one atom. And this atom will be the number 1 in the list below. So one atom, it will be the number 1 in the list below. And I go to define some number of orbitals. For example, 2. The first one could be the 4s. So it's N and L, you know. So by default, it would be 2 electrons. And the 3D, second one, it's 3 electrons, I think. Yes, for vanadium, it's 3 electrons. Yes. So that's the default. In fact, it's what is done automatically in the code. Now, if you want to charge the atom, but you can play. For example, you could try just a 2 electron here. In that case, it would be 1 plus. Because most often when we do that, it's a mistake, the program will stop, saying that, okay, it's not possible because it's not neutral. So I have added a keyword, which is, I think it's, say, free, charge free. Okay, I would have to check. So in that way, that will not stop. Okay. It's just a way to say that even if the molecule is not neutral, code must run anyway. Okay. Now, I already know that if you do that, it won't be good. Because the one who, these one are the 3D are the localized orbital, and they are really inside the absorbing atom. But the 4s are long-range orbitals. Radius is typically 1.5 angstrom, things like that. The 3D are typically 0.5 angstrom. And in fact, the 4s are nearly on the absorbing atom. And when I calculate in the code the potential, in fact, they consider where are really the orbitals, the electrons, if you want. And in practice, if one 3D material is up to 2 plus, in fact, I don't change the configuration. It's from 3 plus that I change the configuration. And in that case, if it's 3 plus, I would write like here 3D 2. So it appears like if it's 1 plus, but in practice, it is what gives the best result to do that. Okay? So it's just a pragmatic. I have often questions about that, in fact, and it's my rule of thumb, I would say.
Okay, thank you very much.
Okay. Okay, bon. I suppress that, CSCF. Okay, now we could change, so I suppress that, edge. Maybe we could see some XAS phenomena. What changed? So we could first run up to a higher radius. So I add a point up to, I don't know, 300. Maybe, but I don't mind about Orbital. But I can let that matter. Okay, so we run this again. Don't forget to save. I run again, so it's done. Fine. Okay, that goes further, so it's done. Now, it could be interesting to see what happens if we change the interatomic distance. For example, we could make some contraction of 3%, something physical. Like in XAS, if you want to fit the interatomic distance. So if we contract by 3%, we could write in place of the 0.97, but more simply, I could write 2.0, 2.1. It's more or less 3%. I don't. It's not to be precise. So I write just to remember. We save, and we run again. And now we go to plot I have too much things. Both calculation. So I go to plot the convoluted one because I'm not interested by the details. So they are here. So this one is the contracted one. So to remember, I write in the title this. So I plot them together. So you can see, so they look rather similar, but here it's different. I zoom a bit. So it looks a bit shifted, but in fact, it's not a shift. It's like an expansion. You can see here it's nearly at the same energy. Here you have, I don't know, some EV, and here some more difference, and so on. So it's the so-called Natoli effect, the guy who defines this effect, that if you contract your sample, this makes an expansion of the spectra. And it's very well known so in XAS. So it's due to the fact that you have an exponential, if you consider the scattering, of k, the wave vector of the photoelectrons, up to a distance equal to r, some distance of the first shell, for example. And to have the bump at the same position, if you increase r by some value, you have to decrease k to have the same effect. So, and k is the square root of the energy. So you can understand by this way that if you contract your sample, it will give an expansion of your spectra. And you can also understand by this way that XAS is better than XANES if you are interested only by the distances of the different shell around the absorbing atom, because higher is energy, more difference you will have in energy between the different bumps. Well, of course, you have to hope that you have no other edge or other damping effect making this too small to see this difference. Okay, so it was just to make this connection with XAS, but now we are, in fact, in XANES more interested typically by the 150 first EV. Okay, now I go to see different things. Maybe I suppress all this energy range. I go back to 2.16 like before. And what I could change the absorbing atom. For example, I go to calculate iron in solution. So atomic number is 26. Well, I keep it in my I don't change the name of it in data file. It's not very correct, but it's easier for us. And it's interesting to see what we get. I save. I run again. The new one is here. I run. Okay. So the new one is iron, and the previous one is vanadium. So there are some difference here. But after you can see the shape is roughly of the same kind. So it's because it's an octahedron. Of course, the edges are not at all at the same energy because it's iron edge versus vanadium edge. But anyway, it's interesting to see that it's typically the same kind of shape. So it's typically of an octahedron. You can see that the shoulder is smaller than here. And if you would compare with experiment, you could check that it's the same in the experiment, that it's smaller in iron than in vanadium. The fact that the intensity is smaller here is because it's not normalized to 1 like in the experiment, but the unit is megabarn. It means that the probability to have the absorption is iron is smaller than in vanadium. So it's something true, in fact. Okay. So it was just to say that the shape depends a bit, but not so much on the atomic number. Well, it depends. Anyway. Okay, now we could change to have more feeling about what happened. We could see what happened if we make some change in structure. For example, we change again, and we go to consider copper in solution, and copper, so it's 29, the atomic number. And copper like to be a Young-Taylor material, giving one long long bonding and two short. I don't remember exactly what are the values. Yes, I have. So I remember, I've noted, I don't remember, that in that case, you have one long distance, 2.18, and two short. And I think it has been seen by XANES, so this. A long time ago. And we could calculate this. Well, I don't consider quadruple because I don't mind. Okay, we run. I don't forget nothing. I take the convoluted spectra like before. So we will have the series from vanadium to copper. So you can see it's even lower than the previous one. So it goes versus Z, we go down. And but it's anyway roughly more or less the same kind of shape. But here it's broader than in iron. So because it's broader, we could check why it is broader. And if we look better, if you look with attention and some feeling, maybe there is something interesting to see in better details. To see in better details, I can also check the not convoluted files. So sometimes it's interesting to see the not convoluted file because you can see details not appearing in the main calculation. And in that case, you can see if I focus, if I zoom, in fact, there are two bumps. Okay, and because of the convolutions, we don't see so much this shoulder here. Okay. So to explain this, maybe I could see what happened versus the polarization. Because you see here, in fact, we have just an average XANES. But if we could imagine that we could fix a molecule versus a specific direction with its solution, so just a numerical experiment. But if you have a crystal, it could be the case. If you have just a surface with molecule adsorbent on it, also you could fix in a specific position your different molecule and study all this versus polarization. So, for example, it could be interesting to see if the polarization of the incoming field is versus Z. We could think that the result will be different than if it's in the basal direction, so versus X, Y, or between them. And to check that, you can use the keyword polarized and define this direction. It's one calculation along X, and next line, one calculation, no, it was Z, sorry. And the next line, one calculation along X. Polarization is along X, so along 1, 0, 0. We could also calculate, for example, along 0, 1, 0, but very probably it will be the same because X and Y, you can see the same. But just to see, we could see along this diagonal that is between in the diagonal between X and Y. So it's less evident to see if it will be the same or not. Okay, so we run this. Now you have more columns corresponding to all this output. So I take the convoluted one. Now you can see the name of the columns are here. So maybe these two ones, we thought that they could be equal. No, it's not this one. It was this one. And indeed, they are equal. Huh? Along X and Y, the same, it's normal. It's the same symmetry. But in fact, also this one. You see? So you can be anyway, in any way in the basal plane, it's always the same. But on the contrary, if you are along Z, it's the other situation. Okay, so if we look at this first bump here, correspond to the polarization along the long direction, along C or along Z, and the other one correspond to the polarization in the basal plane. And in fact, because it's in solution, it's the average between the three directions along X, Y, and Z. So the weight of this bump is 2 times the weight of this one. And okay, here it was easy because we know the solution result, but to help the user, I have put this keyword polarized. And if you don't write anything below, the code automatically do for you this analysis versus the non-equivalent directions. And indeed, so I have just let polarized. There is 3 columns. Output are here. I have not changed the name. And you can see that the code have detected that you have 2 non-equivalent directions, X and Z, and Y would be the same. And here you have the average with a good weight 2 for here, or 2/3, and 1/3 for this one. And if you plot, indeed, you have the same than before. So, okay. So here you can see you have all your explanation. And now, if I, to finish with this part, if I go back with vanadium, well, because now I would like to check for the quadruple. And in copper, in fact, there is not so much quadrupole in that case because they are nearly full the 3D level. So I'm back to vanadium. So at 23, it was 2.16. So, no, first, there is no quadrupole. There is no quadrupole. We saw already that for copper in the basal plane, it was the same. So in fact, maybe I don't make the calculation that without quadrupole, if we have a cubic symmetry, it will be all the same. Okay, it's something very important. If you have a cubic symmetry in your material, signal through the dipole is isotrope, whatever is the direction of the polarization, not only along A, B, or C, but along any direction, you have the same result. But as you will see, it's not the case for the polarized, for the quadrupole. And okay. Well, if I want to check by hand, so I can do in that way. For example, I put one polarization along X. And because it's quadrupole, I also have to define the wave vector. Wave vector must be of the photon, must be perpendicular to the polarization. So I put it along Z. No, sorry. I put the wave vector along X. But I will explain after why, because I know the result. Now I make a rotation by 45 degrees. So polarization is in the basal plane, but along this diagonal, and this one also in the diagonal, but perpendicular to the other one. Now, if I write this without the wave vector, in fact, I will have just the dipole part for this one. So I do that. Polarized, polarization wave vector, polarization wave vector, polarization only. Donc, for this one, I will have just the dipole part. I call it IO6. But I use a not convoluted one to see better because it's wrong. So I have so you can see the name, new plot. So we see the blue, so it's a dipole, but the other are below. But now you can see with this polarization and wave vector, I just probe one of the just the T2G state, and with the other conditions, rotating by 45 degrees, I just probe the EG state. So in fact, I knew the result. It's why I've chosen that way my direction, of course. But so for the users, if you don't know so much the things, you can just do that, and the code automatically for you, like for the dipole, will calculate the non-equivalent direction. And indeed, I save, I run. Up. So in that case, the code, I've calculated the two non-equivalent directions. So it's the same way that we have calculated. And you have also the average with the convenient weight. So it's the same result than before, in fact. For nearly the same, because the average is what you get when you don't write the keyword polarized. Okay. Do you have a question about that? So it's well, interesting for people who are should vary by physics, I would say. Okay. Well, now let's go to things a bit less technical. So what happened if we make some other distortion? So we saw what happened if you have a Jahn-Teller distortion, so it becomes tetrahedral, like in the copper oxide. But just for fun, we could, for example, try to lose the center of symmetry, because it's very often interesting to see what happens if you lose the center of symmetry. So I keep the quadrupole. Maybe no, I don't keep quadrupole. But I don't keep polarized. But I don't mind about the quadrupole. You can keep. But I'm not interested by polarized because it would be too much output. So to lose the center of symmetry, well, you could displace about the atoms as you like. But I go to move a bit the central vanadium. So it's not necessarily at the center, but it mustn't be too much, because you have to think that 0.15 here is multiplied by 2.16 angstrom. So it's already nearly 0.3 angstrom. So it's rather a lot. Huh? So it must remain possible. I don't know, for example, this. And I don't know for anything. No, it's too much. Okay. So now I will have no symmetry. So I write C1, no symmetry. We run. Up. It's here. I plot. And we see that. So my distortion was a bit too much, maybe. I can compare with the other vanadium. Versus. Okay, so well, the distortion was a bit too much. But okay, it was just as a test. But what is important, I wanted to show you, is that when you lose the center of symmetry, you get a big pre-edge. So it's something specific. Without center of symmetry, you always have, for nearly always, have big pre-edge. And it's very useful because sometimes it's this 8 here versus the 8 of the edge. Sometimes it's used to measure the loss of center of symmetry. If you have some absorbing atom, not exactly at the center. For example, there is a way to lose the center of symmetry. It's just to increase the temperature. If you have some material with some octahedral environment, you can have some very small pre-edge due to quadruple phenomena, but very, very small pre-edge. And if you increase the temperature, it's a case, for example, in titanium dioxide, in rutile. In fact, pre-edge increase. It's due to the fact that now what you see are not only the quadrupole effect, but also some dipole effect. In fact, this pre-edge is dipole. It's why it's big. A quadrupole, it's always small. And why the pre-edge increase here is because you lose the center of symmetry. You remember that at this energy, you had the pre-edge quadrupolar. So the one probing the D state. So because you lose, so here you have D state. And because you lose the center of symmetry, now you can make a hybridization between P and this state, that is odd and even state. And due to this fact, p state like quantitatively more to be at this energy because they can harmonize to the d states which are close to the Fermi level. And because dipole channel is more easy, it's give more intensity than quadrupole channel, even if you have only a small amount of p state, anyway, the bump corresponding to this transition becomes far more important than the bump corresponding to the quadrupole part. Okay. And by this explanation, this shows that if, so you need to have this state in the non-occupied state, because by this way, you can see them with the XANES. And so you can see eventually the hybridization with p state. But if you were, for example, at the zinc edge, which is 3D10, if you have not the center of symmetry, the hybridization occurs, but it's in occupied state, so you don't see a pre-edge at the zinc edge. But for all the other edges, if it's not 3D10, copper sometimes it can be 3D10, but you have a pre-edge if you have not the center of symmetry. Okay, so pre-edge is very, so even if it's small, pre-edge is very important to check because there are many details, interesting details. Okay, so I have a whole little program. So if you have some, if you would like I calculate different things, so you can also ask, maybe just after I show 2 or 3 other calculations. So now I go to change to make calculation with crystal. So for example, iron 304. Okay, I go to okay, so we okay. So I go to iron 304. Here is in data file, so it's ready for this first calculation. So it's more or less what we saw in the presentation I did at the beginning. But here I'm not interested by the DAFs, the resonant spectroscopy, so only XANES. So it's more or less what we saw before. You can see that there are 2 non-equivalent iron atoms, and I know, because I know magnetite, I've worked already with magnetite, that this one are octahedral iron with an octahedron of oxygen around it, slightly distorted, and you have 16 equivalent octahedron, 16 equivalent iron, and this one are tetrahedral iron with 4 oxygen around, and of course you have different oxygen, and you have 32 oxygen. Okay, so this in data file is ready. You can see now the radius will be important, and indeed we go to check what happened versus the radius. So we start with a small radius. Well, now, because it's another in data file, you remember this file, FDM file.txt, we have to change the name. And because, okay, we change the name of the data. The name and the name of the directory, or the path. I save. Yes, I didn't mention. So in doc it's a traditional doc of the when you download the code. But here are the doc for the practical. So you have the presentation I did at the beginning. You have a chapter I've written in a book about theory of X-ray absorption near edge structure, and here is what we are doing right now, more or less. Okay, and okay, so I go back to Iron 304. But in fact, it's ready for the first calculation. So I just run, so you can see it's Iron 304, radius 3. Okay, so you have one run, you can see. And then the second run is starting because you have two non-equivalent absorbing atoms. So there are two calculations, independent calculation. And you can see you have two groups of output files. The one with _1, it's the first absorbing atom. So in the list, it was, I know that it was the octahedral one, the convoluted one. And then for the second iron site, which is a tetrahedral site, I know. And of course, the sum, because at the end, if you want to compare the experiment, you must have the total signal. And note that, in fact, we had this keyword all conv, because if you don't have it, this keyword, you would not have the convoluted spectra of the individual site. So sometimes we are not interested by this, but here it will be interesting to see the difference. So let's compare these three files, the one for the octahedra, the one for the tetrahedra, and the total. I have to put them. Donc, the first one. Okay. So here you can recognize just by the shape the octahedral site. Typically the one. Here, the shape is very different, and you have a big pre-edge. It's the tetrahedral iron. And indeed, in the tetrahedra, you have no center of symmetry on the absorbing atom. There is one in the unit cell, but you have no center of symmetry on the absorbing atom. And so you have a big pre-edge if you compare to the main edge. Now you can see that the intensity, it's about, for the cross-section, is about 0.2 megabard here, but here it's a double. So it's due to the fact that it's not average, but it's sum over all the equivalent atom. And in fact, in the unit cell, you have 8 equivalent iron in tetrahedral site. On the contrary, for the octahedral site, you have 16 equivalent atoms. So it's why it's two times more atoms. So you have 2 times more intensity. And the total cross-section, so it's just the sum. And it's why it look more like the octahedra, just because the weight is 2 times the one of the tetrahedra. But the pre-edge is mainly the one of the tetrahedra. And that's very interesting because, for example, people have studied doping of other elements in iron. For example, you can put a cobalt as doping element with, well, eventually rather large amount of doping, and you can have an idea of where come the cobalt doping element. Is it on the tetrahedral site or in the octahedral site, just looking at the pre-edge or the ratio between the pre-edge and the main edge. So you can get an idea by this way of where come some doping element. Okay, now maybe we use a very small radius for this calculation, only 3 angstrom. So it could be interesting to try higher radius because we have to go up to convergence. So we always do in that way. So I have also the green keyword because to go faster. So now I change both, just the radius and the name, of course. I run again. And maybe to save some time, I immediately, because more large is the cluster, more large is the radius, more long is the calculation. So I immediately calculate. You can see it's a bit longer. So I have saved. I can send another job at the same time. It's not a problem. Okay. Now, maybe, so it's running. We could have a look at the BAV file, this underscore BAV file. So in fact, you have many details. BAV, it's a 3 first letter of a French word, which is bavard. It means talkative in English. So it's, in fact, you have many details on the calculation. So you have your in-data files, which are more or less recalled, all what is default. You have all the atoms in the unit cell, not only the non-equivalent one. And you have after the symmetry under SymSite between all the atoms. So you can see that here you have 16 atoms of iron and their position in the unit cell and the relative symmetry between them. The same for the octahedral site, tetrahedral site, and the same for the oxygen site. 32 atoms and their position in the unit cell. I show that because when I make a new calculation, I always check this part to be sure that I didn't make some kind of mistakes. And the most important, in fact, to check is a bit further. In fact, you look at for this word agrégat, which means cluster in French, but it's also written cluster a bit later. So if you look at for cluster, if you prefer, you can find the word cluster here. So this part is very important because when you make a mistake in the data file, in the atom position, it's very often here that you can check. So I always check. So first here, bon, it's for people who know about group symmetry, but you have the point group of the atoms. So this one is minus 3m. So in fact, it's a specific symmetry. And I means if there is a one that you have a center of inversion. And here I listed all the symmetry operation and so on. But the most important is here. In fact, it's the cluster around the absorbing atom. And you can see that, okay, you have your iron at the center. Then you have 6 oxygen atoms. It's versus the distance to the central absorbing atom. So you have 6 atoms at 2.05 angstrom from the center. So it looks like an octahedron. And after, you can also check where is your following shell, the following one. So our iron atom at 2.96 angstrom, and so on. So you can check the different shell. very often when you make a mistake in the data file, and sometimes the mistake is not from you. For example, you have imported a file, a CIF file or something like that, and sometimes some refinement are not good, or some you can have many kind of mistakes. And if, for example, you find some position which are not possible, for example, two atoms at 1 angstrom of distance or things like that, very probably you have a mistake. So for a new study, I always check at least one time at the beginning if there is a mistake here. So here you have the distances, and a bit further, you have the angle between the central atom and the two neighboring atoms, the number 2 and the number 3 in the list above. So you can see 87 degrees, so close to 90, in fact. Or this one are in opposite sides. So you can see with number close to 90 or 180, it looks like an octahedron, slightly distorted, but anyway, it's an octahedron. So we have checked that it's indeed an octahedron. And if I go further, I look for aggregate. So it was the first absorbing atom, and now I have the second absorbing atom in my list. Point group is very different, -4 3m RTD, so using the Schoenflies notation. So it's a tetrahedral, you can see with the T environment. There is no center of symmetry. And if you look at the atomic position, so you can see you have only 4 oxygen around the absorbing atom at this distance, a smaller distance. And after you have the following shell. So you can see with the radius 3, for this one, we had only 1 shell. So it was not a lot. And with the radius 4, we did after, we have we have 33 atoms. And with the radius 5, we have 45 atoms. I don't know how many shells. And after you have the angles again between the bond, and you can see it looks like a tetrahedral angles. Okay, so all the calculations are done. So maybe I go to check only the total signal for the other radius. Donc, R4 and R5. Oh, I write R4. R5. Okay, so you can see that it's rather different. So it's easy to see that radius 3 it was not sufficient. And if you would compare to experiment, you could see that this bump is indeed here. Between 4 and 5, there is not so much difference, but there is some. So also a shoulder is appearing here. It's also in the experiment. And okay. And typically in iron, it's already not so bad here, but we could go a bit further, 6 or sometimes even 7. It would be the best. But anyway, there is not anymore so much difference from here. What you can note also is that the general shape of the signal, so the one with a very small radius, was not exact, of course, but anyway, it's not completely bad. So it means that in one calculation, you have the experiment. If there is nothing to do with the experiment, it means that there is a problem. Well, even if the code is not perfect, of course, simulations are not perfect. I do not pretend that. But for a K edge or a L23 edge of a heavy element, results must always look like the general shape must look like the experiment. If there is a big difference, there is a problem, and so you can have done a mistake in your in-data file. And the most often, what happens is, in fact, in the structure. So you must absolutely check that. If it's completely very, very different, there is a problem. After, if you want to fit perfectly the pre-edge and so on, okay, it's hard. Very often, the position of the pre-edge is not perfect. It can be, in the simulation, rather often it's at a bit too high energy versus the main edge. So there are some difficulties sometimes. But roughly speaking, it must be convenient. Okay, so it was to C versus radius. Yes, there is one thing I've not spoken about. If you compare to experiment, I didn't spoke about the broadening. But I have some parameters for the broadening, which are mostly by default, and not all. In fact, the broadening is due to the core hole width and to the final state width of the photoelectron state width. For the core hole, in fact, the width, we use the one from the table, I forgot the name. So it's a very famous table giving the width of the core hole. So in fact, you cannot change this parameter, even if it's a parameter. But if you make experiment using high resolution fluorescence mode, you know, HERFD mode. In that way, because you select the energy, you select a thin width in energy in your measurement, you have to decrease this width. So I go to show how to do that. Maybe, yes, we can do with iron, why not? So to change, so I could write anywhere in the data file. This I don't use. So to change the width of the core hole, so the keyword is gamma hole, gamma underscore hole. If you want to know what is the value by default, in fact, you look at in the BAF file, it has been calculated. And if you look at the bottom, here are the default value. So it's for iron, it's 1.25. Okay, so it's to get an idea. And gamma max, it's another parameter. It's for the width of the photoelectron state at infinite energy. So, for example, typically we could have 0.7 EV. I don't know if this will give a lot of difference. So you could do that. So you can run all again and with this keyword gamma hole. But in fact, it's not so much clever to do in that way because sometimes calculations are long and the convolution part is very short, in fact, on the contrary. So it's possible to in fact, to build a new in-data file to make only the convolution. Well, I write it in that way. Save. So now, because it's only the convolution, I don't need all that. That's only comment. And here, in fact, to call for the not convoluted file, I write the keyword calculation. and below the name, for example, this one. So if I do that, it's very fast, in fact. So now it's another data file name, so I have to change. You remember in here. So now I run. Okay, it was very fast because the convolution is fast. So I go back here, and I will have the new output file. You saw it's written that gamma hole now in the name. It's written. It's helpful. And if we compare both files, the new one, and only the one with radius 5, maybe. Okay, oh, it's not very different, but okay, it's a bit more resolved, in fact. And you couldn't do the same. For example, changing you could also change gamma max. So you saw the default is 15 EV, and I know that it's a bit too much. So my default value is a bit too much. Let's put a 10 EV and see what happens. I do the test with you. I've not checked it before if it's good or not. So now you have this new output file. We like gamma max 10. So it's no, it's not. It's not. It's the output only for the tetrahedron, because there is the _2 in the name, so it's not the total. It's this one. Okay, so it's less convoluted, as you can see in this part. Okay, and to finish with that, note that for the extended part, rather not like XAS, but in fact, it's also possible to consider the thermal effect, and it's done with the keyword apps u iso. So it's the isotropical thermal displacement, and so if you would write this, it's too much because it's in Ångström square. You could have some thermal effect, but it's a secondary effect, in fact. So these three, gamma hole, gamma max, and apps u iso can be changed so to be closer to the experiment also. Well, this part is more for the publication at the end, when you want to be the closest possible with the experiment. Okay. Okay. I finished the most important things I wanted to do Well, I have other possibilities, but I would like to know if you would be interested. I tried special things, or do you have some questions and so on? So please tell me.
So to me, it was very clear. Thank you for the great teaching experience.
Well, okay, so if there is no, because it's not, we have still time, so I can continue anyway.
Yeah, could I ask a question?
Yes, please.
Yeah, I wonder how to calibrate the energy. I noticed that the edge now is about 0, and yeah, if we want to, to compare with different samples, how to do the energy calibration? Can we also compare with the standard samples?
Yes, thank you. Very good question. So the first things is that, as you can see, the results here are in the photoelectron energy, with the 0 being more or less the Fermi energy. So first, in your data file, it could be in the convoluted part only, but if you would add the keyword, I think it's energphot, the edge energy is added to the result. I'm not absolutely sure it's energphot, but I think it's that. A little doubt. It's energph. Yes, I think it is. So in fact, you just add the edge energy. Okay. Note, I never use it, in fact. Note also that the edge energy are written, in fact, in the first line of the not convoluted file are written this edge energy. So if you want to get it. But anyway, if you add this energy, usually, nearly often, you have anyway some EV of differences with the true edge. So why? There is different reasons. So first, calculations are not perfect, evidently. And the second one is that the edge position is defined in a specific way in experiment. And I think it was used as a point where the slope is maximum, something like that, in the main edge. And in fact, this point very rarely, not often, correspond to the Fermi energy. So it's very difficult to, so it's rather artificial, I mean. So it's from the calculation point of view, it's difficult to perfectly fit something which is rather artificial in the definition of the experiment. So this means that you nearly always will have to make a shift between the experiment and the simulation. Nevertheless, if calculations are well done, and if you study your material versus some parameter, I don't know, different oxidation state or different, or the same absorption edge, but for different compounds, in principle, the shift to perform at the end between experiment and theory would have to be always the same. Okay? So, okay. Now, how? So, suppose, for example, that you have a reference sample, which could be metallic, for example, and now, so you have measure it, and you did also the experiment on some oxide, for example. So the same element in some oxide. Oxide, for example, 1 times 2 plus, another one would be 3 plus in another compound, things like that. So we know that this gives a shift in the experiment of the main edge. Normally, if the calculation is well done, even if it's not perfect, but I've already published about that. So it's possible to reproduce rather well these relative shifts between different oxidation states. Okay. So at the end, if all is well done with a unique shift, if you have defined a shift for the reference sample, it should be the same for all the other material. Okay. Now, to do that, there is one thing more to do. In fact, because in fact the edge energy for the experiment don't depend only on the states above the Fermi level. In fact, it depends also on the core state. If your material is oxidized, you need more energy to go from the core state up to the final state, because the final state is modified, but also because the core state is deeper. Okay? So in fact, we have to consider in the simulation, if we want to reproduce that, also the fact that the core hole versus the Fermi level is not at the same energy, depending on the oxidation state. Indeed, if your metallic atom, for example, lose some electron to go towards the neighboring oxygen, for example, potential decrease, and so the core level decrease in energy also. And so you need more energy to go up to the final state. So it means that to make the comparison, you need to consider also the shift of the core state. Okay? That's possible. And now if you look again, the first line here, you have many number, and some of them, so we have to count. It's what they are called EPE. It means energy du psi initial. It's not a very good name, sorry. But in fact, it's the energy of the core state. Okay? It's not the total energy here, but it is the energy. And in fact, this number, it's this one here. So now, if you make this calculation, for example, iron 3+, and you would make another calculation with iron 2+, I don't know, another material. It could be hematite, which is only, in magnetite, you have the tetrahedral site are 3+, and the octahedral site are 2.5+. Okay. But if you would calculate hematite, the calculation is independent. First, I have to mention that because in this structure, iron 3O+, you have two kinds of iron with different oxidation state, and so both edges are slightly shifted, but it's automatically done in the calculation. The shift I was mentioning about due to the core edge between the two sides is automatically done for you. Okay? But now, if you make two independent calculations, it cannot be done automatically for you. So it's why you have to give a reference for this core level. So what you have to do is to first make a calculation with your reference. You search for this number, but in fact, you have also it in the BAF file. So let's go back to the BAF file. In fact, it's easier to see. So it's so my name is a bit horrible. Sorry, it's EPSEE. So it's a number. So in fact, you look for this number, okay? So I copy. And now you go in your in-data file and you say, okay, I have a reference. So you can write in any place. In fact, it's done at the convolution step. Huh? But just above you write EPE, and that's it. So, okay, so to summarize, to compare with experiment with best possible shift, I would say, between experiment and simulation, you always have a shift to perform at the end, but it must be always the same if you use this procedure. So first a calculation with one of your sample, one of your in data file, you write the value of psi I, and after you report it in all your calculation with all your structure you are calculating. And so it will be automatically shifted by the difference between this value of the reference and the new value calculated in what you are calculating. Have you catched more or less?
Yeah, thank you very much. Yeah, thank you very much.
Okay, so the idea was just to have the shift of the core level. Yes, okay. Yes, and I forgot to mention, and if you want to be precise, especially if you compare different oxide, calculation must be self-consistent, because otherwise the electronic structure is not sufficiently well calculated. And so you must have written SCF somewhere in all your calculation. Voilà. We did that, for example, for different kind of manganese oxide, and so it works rather well, I would say. Okay. Okay. If there is no other questions, I could maybe I could mention how to make a calculation with some magnetism. I don't know if some of you interested by this or not. Oh, well, I have a very simple example, nickel. Simple nickel. In fact, to say to the atom that it's magnetic, you have a specific keyword to give. You have to define the fact that you have not the same number of up and down electrons. In that case, I take nickel, so nickel is 3d8, and with the keyword atom, I can define 28 for nickel. I go to define one orbital, which is a 3d1, and I put 5 electrons up and 3 down. And because I've used this keyword, in fact, now I don't write anymore the atomic number 28, but I write 1 just to say that is the first atom. It's the first line under atom, because we could have different kind of atom and have another line with another atom. So we would have another index. So with this, your atom is polarized in speed. And to be magnetic, you also have to add the keyword spin orbit or magnetism. If you write just magnetism like this, so calculation will be magnetic, but in fact at a k edge, it's you have no effect on dichroism, because to have dichroism, XMCD, X-ray magnetic circular dichroism, we need spin orbit, and at the k edge, the core state is L equals 0, it's 1s, so you don't have spin orbit. And with the keyword spin orbit, you put some spin orbit in the final state, so you can get some XMC. But at the L23 edge, in fact, there are spin orbit already in the core state, and so magnetism can be sufficient. Spin orbit would be more precise, but magnetism could be sufficient. So, okay, here I just write the magnetism. So we could write this. Okay. So, save. So I have to change my in-data file name. Now it's nickel. Okay. I forget to mention something. To say that we want to make X-ray circular polarization, I use this keyword polarization. It's the same than polarized. I use a different way to write it. So it's the same that what we saw before. Well, in fact, we don't need that. But we could. So if we have just one OO, it would be just a polarization along X, as we saw before. But I have a way that if you write the keyword, if you write the value of polarization like 0, OOO, and then for the wave vector you write OO1, the code understood that it will be circular polarization around this direction. So along C. So maybe this I don't need. Okay. Well, anyway, so it's already calculated. So, okay, so we have the result. Up. So you can see that, so here it was the first polarization that I've suppressed at the end, but it was already calculated. And it's not useful because when you do that, the code automatically calculates left polarization, right polarization, then it makes a sum, the half sum, so it gets the classical absorption along this Z direction, and then the difference between left and right, or right and left, I never remember. And so you get the dichroism XMCD around this direction. So let's plot them. So you can see it's the L23 edge, so it's the S3 edge, it's the L2 edge. So if you remember my presentation on metal nickel, it was, so you can see it was a white line I showed before, but then that doesn't go back to 0, then the L2 edge. And so it's not so bad, in fact, because it's a metal, it's not an oxide, but there is something which is not here. In fact, in the experiment, there is a little bump here, which is a multi-electronic phenomena, which is not possible to see in classical DFT calculation. But anyway, the main agreement is not so bad, I would say. So this one is a simple absorption, and this one is a dichroism. So the difference between left and right polarization. And okay, so it's typically what we get. You can see that the ratio is not -1. It's due to the fact that usually one says that the difference is proportional to the orbital moment, but it's not so true, I think, so, for different reasons. Okay, so it's possible to calculate magnetic sample. Maybe another thing, yes, I've forgot to speak about one thing when I've calculated iron. In fact, so here we had calculated. So I go back to a smaller radius to go faster. So I have a 3 angstrom for the radius. No, I'm not. So suppose now you want to calculate the edge of a doping element. I mentioned that, for example, it's possible to have cobalt atom which come in substitution with iron atom. And the question is to know, does it come to the octahedral side or the tetrahedral side? So it's possible to test this. So in that case, you write the keyword doping. And it would be cobalt, for example. Bon, cobalt is 27. And so after, it can be or in the first site, octahedral, or in the second site, tetrahedral. So to do, so you have to choose. And for example, if you choose the first site, you write 1. So in that case, what you go to calculate is the cobalt edge. That's it. I save. I go back here to I save. We run. So it's a good one. So if you look at the BAV file of the last one, it was, you can see. So if you search for aggregate, we can check the you can see that now we have the cobalt atom at the center, but around you have only oxygen and iron. So the difference is only that this put the cobalt atom at the center. So it's a small amount, and it's a small doping amount. And so if you can plot, and because it's at the octahedral site, of course, it looks like an octahedral site, but it's cobalt. In fact, it's not iron. Okay, so I think sometimes people like to calculate this kind of. After, if you have, if the doping is too much, for example, you could have some structure with 30% of some element and 70% of other elements. And in fact, in that case, often it's better to make a superstructure. So you build a new unit cell with a superstructure. It's possible to do that with a code and to mix a bit the different possibility of atom in some average way that you choose yourself. So it's more precise. Now maybe some words how to improve a calculation in general. So for example, I'm here with my element. So I've calculated iron. I'm not so happy with the result. So the first things, always the first things to do is to start calculation with green keyword because it's faster and with a small radius and without cell consistency. You do that. Then you have a spectra. You compare with the experiment if you have. If you have not, you cannot compare. So as I said at the moment, so the result cannot be excellent, but at least the general envelope of the edge must be okay. If it's the case, then second step, you start to increase the radius. And typically, you can go up to 5, 6, 7 angstrom. It's very, very rare that you have to go beyond that. And in fact, it depends on your sample geometry. If it's very well ordered with atom well aligned, for example, a perfect CFC symmetry, you know, in that case, you need because the photoelectron like to go through the atoms in a perfect way. So you need a higher radius that if it's rather if the atoms are not well aligned, if you have some not exactly disorder because it can be a periodical system, but if you have a metalloprotein, you can calculate a metalloprotein if you want, but the atoms are not well aligned, and usually in that case you need a smaller radius. It can be sufficient only 4 or 5. Okay, if you are not happy at this stage, you have to start with self-consistent calculation. So you put the keyword self-consistent, and as I said before, self-consistent calculation can be better only if your structure is good or not completely bad, I would say. If some, it's very important because when we search a structure from the CIF file, we don't know how these files were produced, and some atoms are missing. For example, in CIF file, because the hydrogen atoms are difficult to see with X-ray diffraction, X-ray diffraction, sometimes they are simply not in the structure. So if you make a self-consistent atom without all the atoms, it will be worse than with a self-consistent calculation. So, but anyway, so if you are confident with your structure, you have to perform a self-consistent calculation. For metallic system, it's not so important, but if it's oxidized or things like that, it's more important. Indeed, you have to do that. Okay, that's already the main points. Now, so if you are very interested by the pre-edge, it's rather difficult to have the pre-edge exactly at the convenient energy. It's very difficult, but to improve that, sometimes, in fact, when we have the keyword SCF, the self-consistent calculation is done in the ground state. Then, for the calculation of the XANES, just at the end, I put the core hole plus an extra electron into the first non-occupied level. So, in some way, only the absorbing atom is excited. So it's an approximation. I found that I do that because I found that it was very often the best, but maybe not always. So if you want that your self-consistent calculation is done with the core hole, you have to write the keyword SCF-EXC, like self-consistent field excited. Okay, so it's a next step. If you are still not happy, so I said that the self-consistent calculation without SCF or without SCFX, in fact, the core hole is considered, so you have the core hole plus a screening electron, a full screening electron is the first non-occupied level, but it can be that the screening electron, it's too much. And so it's possible to decrease this screening. So the keyword is screening. So the default is 1. So if you do that, this doesn't change. I forgot the G. But so it's a default, but you can try smaller value. You can try 0, simply 0. But you also can try 0.5 or value like this. I find for titanium dioxide, 0.5 was the best. And this, in fact, gives a shift of the pre-edge, the keyword screening, especially of the quadrupolar pre-edge. And you can also have SCFX with screening 0. Sometimes I do that. Okay. These cases are a bit difficult always. Yes, I have also to mention that for the L23 edge, even for the heavy elements, maybe it's not a good idea in the code, but by default, calculations are done in the ground state. So if you calculate L23 edge of, I don't know, platinum or heavy elements, or 4D elements, or even 5D elements, you can prefer to make calculation in the excited state and not in the ground state. So the keyword to do that is excited. It's for the main calculation for the XANES. So all these keywords are explained in the manual. And I'm not sure about this one, but what I'm just explaining now, it's also written in the part how to make the best possible calculation in the manual. And in fact, that's nearly all. So there is no so much possibilities. Yes, maybe if your material like to be calculated with a U-bar correction, so it's typically for some oxide. If you're interested by some material, you probably know if it could be important for it or not. In that case, it's you put the keyword U-bar, and below it's a parameter in the code. It's a U-bar correction, and the value are typically about 5 EV or 6 EV, things like that. And you run. Okay. In fact, I nearly explained all what you can do to improve the simulation, I think. It's due to the fact that there is some parameter like U-bar, some different way to make the calculation, because we have to mimic with one electrode code some multi-electronic phenomena. But anyway, it's nearly an ab initio code, so there is no many way to modify the calculations. After you can move the atoms, of course, but its problem of structure is different. Maybe well, it depends what you are. Well, sometimes other kind of calculation, people work on cluster, maybe adsorbable on surfaces, things like that. And I can show an example. It's not here. And yeah, Raman spectroscopy, I don't know. Do you make some Raman spectroscopy? So if you do Raman spectroscopy, so it's the same in data file, but there is a keyword. It's for non-resonant inelastic X-ray scattering. And after, it's all the same. And in fact, you have to define the value of Q. You remember this the moment of the transitions. So here we go from 3 to 6. So we have just 2 values. And with this keyword, in fact, you have in the output file all the expansions versus, you have the monopole term, the dipole term, the quadrupole term, and so on. But that's all. So calculation is the same. Yes, I didn't explain how to make an X-ray resonant. If you want to make X-ray emission spectroscopies, so you have to just write the keyword XAS, and so you automatically have the emission. And of course, you have to calculate in the range, most part below the Fermi level, because you probe the state below the Fermi level. In that case, so it was self-consistent, but the remaining is the same. In fact, it's what I show in the little introduction I did. Okay, so I've not spoken about resonant diffraction example and so on. So it depends on you. So, or if you have some, we have 5 minutes more. If you have some questions, so I can answer. So it's as you like. So just tell me if you have a question.
Yeah. Can I ask a question?
Yes, yes, of course.
Okay, thank you very much. And for the X-ray emission calculation and how we define how to calculate the main line or the valence to core from the code.
Okay, okay. In fact, I don't define them.
Okay.
So, but the code is so it just through this energy. You see, if you go at lower energy, if you start at minus, I don't know, 200, that will automatically probe the other all the lines. Okay, but I must say that the code is in fact convenient only for the valence to core, because for the beta, I don't remember, for the one which is below the valence to core, there is some exchange phenomena between the 3D state and this state, just 3P, I think, and it's not included. So it won't be very good for the other emission line, unfortunately. But I plan to work on this soon to improve the code. So it's more for valence to core up to now.
Thank you very much. Yeah.
So, sorry? Oh,
thank you very much.
okay, okay. Okay. Bon, okay, no more questions. So I thank you for your attention. So usually I don't know my tutorial in that way. So it's direct with people. And so it's not at all this kind of tutorial I do, because I'm around the people, they do the calculations themselves. So I think it's better to learn. So here it's a bit complex maybe. So anyway, so if you have questions in the future when you make calculations, so you can send me mails. So it's part of my job to answer to the mails, and I usually answer if I can. And okay. So if there is no more questions, so I thank you for your attention, and have a good afternoon.
Thank you very much.
Yeah, thank you very much.
You're welcome.
Yeah.